online. Well, welcome back. Hello online. Hello in person. Gotta have that YouTube intro. This is the last week of class. And if I go quick today, I might get both of the lectures done today. Would you like that? No. Let me go through the announcements quick though. This is a no BS class today. No jokes, just straight material. Okay? All right. So, number one, you guys got to help me out here. The Hoffman House, I'm losing. All right? So do me a favor and rate the class. Do it right now. For those of you on your computer who haven't done it, if you're one of the 9 who have, thank you. If you're one of the people who haven't yet, now's a great time. I don't care. You can just be distracted. Okay? All right. I also just sent out a Qualtrics survey via email because, as you know, the stuff in the university doesn't have a written section. So if you have the time and were willing to share your thoughts on the class, I would love it. It's anonymous. I sent it to your personal email or your UI email address so that you can only reply once. But I will not be tracking it, and I would love to hear your opinion about what I could do to make this better. It's been a challenge as we started class. It was a challenge this semester, but you know. So if you got an email from Qualtrics that had my name on it, I sent it. Okay? Any thoughts or questions on that? No. Okay, I will grade your homework 3 later this week or early next week. Your project report is due next Wednesday, as you know. We have presentations next Wednesday. Right now we have 7 people signed up, which is fine. They're optional. If you are on the fence about it, you don't have to make a fancy presentation. It can literally be stuff you have, your model, your code, and discussion. It's really low stress. It's built to share what you've learned. That's it. And then today I have office hours after class. Now let me ask you, I know I've had a few of you sign up to meet me between now and Wednesday. I'm assuming about the project. My guess is probably because, let's be honest, I'm not the nicest guy to talk to these days. But would you like more availability from me to help with the project? Does anybody need more time, more interaction? Yes? No? So? Not sure yet. Starting the project this weekend. Is that where I'm at? Understood? Understood. Anybody online? So I'll make you a deal. I'm all about deal making. I feel like I don't know who I am. If you promise me to go rate my class, I promise you after class I will open up some time. I'll just be in my office. You can pop in, or be in the CASMA conference room. You can pop in and we can make it work. Okay? Sound good? Okay. I'll have extra availability through next Wednesday when the project is due. Okay? All right. I know Lisa does office hours and stuff, and I know, and you know I have to compete with her. So, because only I am the one that's competing with her, because she's not competing with me. But, all right, let's just be real. But yeah, I'll do that. I will send out that information this afternoon at some point, or maybe this evening, depending on how busy I am this afternoon. But I do encourage you to come to office hours today. I know we have a GMAS meeting today at 3, but I'll probably have office hours more than just show up at the GMAS. I might poke my head in and say hi at GMAS. But, so office hours up from 2 to 4, so I do encourage you to use it. All right. Okay. Any questions for me? All right. So as I've mentioned, if I make it with no stories and no BS and no jokes, we can get through both lectures today. Do you want to? With more time for project? So I won't prepare anything new for Friday. All right. I just don't have the time to make that. And I have PTSD from getting Stan to work just in time to make slides and talk about it in class. So today we're going to talk about latent variable scale identification first, and if we get done with that, we'll talk about model fit. Okay? Scale identification. Remember last Friday we discussed empirical priors. What's an empirical prior? A prior that has hyperparameter, at least one hyperparameter is estimated from the analysis itself. Last time we saw, when we set a prior on, let's say, factor loadings, the lambda parameters, we can, instead of having to specify a mean and a variance for each, we can just estimate it. we talked about some of the pitfalls of it. We left off last time saying not every parameter works that way, right? And the thetas, latent variables, are where the problem really lies. So if you wanted to set an empirical prior on your thetas, I showed you at the end of class last time, it was really difficult because you didn't get convergence. The rationale, the reason for that is theta itself needs to be identified more than just by setting the prior. The model data likelihood is not identified without some constraints on the latent variable or some parameters to make it work. I won't show you mathematically why that is the case in here, but it is the case. I think I'll probably save that for fall's class about multidimensional measurement models. But, so today we're going to talk about if you want to estimate the mean and standard deviation of the latent variable, what to do. You know our data. Today we'll be using a graded response model set again. So going back from last Friday, we talked about things in the CFA world. I'm going back to graded response model for this. Again, to underscore the point that the measurement model part, the data choice, is flexible. It's generalized. Like properties from the model don't change a whole lot when you change them. So remember this. I put this in our slides talking about the general theory of latent variables before. Our models need two types of we need two types of identification to be valid. The first is what I'm calling empirical identification. How many items we need per latent variable. I talked about having 3 as a minimum per latent variable. Technically, you need at least 3 on one factor and a correlated factor that has 2. I prefer that. The other method that we need to identify is what the scale was. Remember, the latent variable itself is not identified. We're basically saying, hey, we have this latent variable. It's continuous. That doesn't enough. We need to define what the mean of it is and what the variance of it is, or standard deviation of it is, the scale itself. And so up to this point, we have set the mean and variance, right? Using what's called the standardized factor method. For unidimensional models, this meant the mean was always 0, the standard deviation was 1. Last week, we got a little crazy with the multidimensional code. We still had the mean being 0, the standard deviation being 1, and in that case, we did estimate our off-diagonal correlations. So long as we have the mean and the variance identified, we can estimate the correlations. And technically, that is an empirical prior for the correlations, right? We're estimating them. So what about the means and variances, though? If you want to estimate means, and sometimes you may, particularly if you are using a simultaneous model, like estimating latent variables and using them to predict other things, or the opposite, using other things to predict the latent variable itself, you may need a variance to predict because it becomes a residual variance after a prediction happens. Right? So if you're doing a structural equation model, a path analysis, anything with latent variables simultaneously, this is where you'll need this. An invariance analysis, actually, also you'll need this in invariance checking, which I didn't cover in this class. Okay, so what do we do? For variances, turns out, if you look at each latent variable in a model, you take one item and you set its discrimination or loading parameter, the lambda, to 1. We call that a marker item for the variance. When you set it to 1, you have enough unknowns in the system of equations so you can estimate the variance of the factor. Now, it's a pseudo-variance, right? It's heavily influenced by the marker item. If I pick the first item to be a marker item and Vladimir picks the third item, we're going to have different estimates of our latent variables variance, but they're transformations of each other. The model, if we were to look at the model data likelihoods, it would be identical, just a transformation of parameters between the two. So it's arbitrary which one we pick, and the variance that we're choosing, or the item that we're choosing, the variance that we pick from it, it's only because of that choice, right? It's like the whack-a-mole of your choice here. So That's for variance. Turns out for means of the latent variable, you can do the same thing. Only now the parameter to fix is the item intercept. So for one item per latent variable, you take one intercept and change it to 0. You can then estimate the latent variable mean. All right? Often this technique is called marker item. In other packages like M+ or Lavon, not in Bayes, it defaults to a marker item for the variance, but a standardized factor for the mean, a mean of 0. So you can mix and match too, right? Again, by default, you pull up M+ or you pull up Lavon, you give it a latent variable model, it sets the factor means to 0. It sets one discrimination or loading to 1 per factor, and it estimates every variance. The reason for that is the field that this came out of was structural equation modeling, where you need that variance to predict. That's where it comes from. But again, these are different parameterizations of the same model. The models are equivalent, and we can even show it mathematically if we wanted to. The model data likelihood is a transformation. When we pick 1 to be a 0, where that parameter's influence goes as the mean now, and it moves things over a little bit slightly. So, yes?
What's the interpretation of these parameters if we are estimating them? For example, if the standard deviation of theta is bigger than 1, what is the meaning of that? Well,
it's just a different metric, basically. If you think of a standard deviation as being the units of measure, right? So if a standard deviation is bigger or smaller than 1, it just talks about how much variance there is. It's a descriptive measure, really. It doesn't change the interpretation of anything else. All the other parameters are interpreted the same. Factor loading is still the increase in the expected outcome, either the link transformed or data, for a 1 unit increase in the factor. Now that 1 unit has changed. So if the standard deviation is 0.1 instead of 1, 1 unit is 10 standard deviations. Right? So it's the same idea that you'd see in a linear regression. So if you're used to seeing standardized factors where 1 unit is 1 standard deviation, it will look different. The size of the parameters will look different, but the interpretation is still the same, and it's still the same that we would use in a linear model like regression or logistic regression. Hope that helps. How we doing? All right. So today, goodness, I'm sorry for this slide here. We're just going to look at the standard deviation side. I will fix my slides. This should be a sub-bullet. To estimate the standard deviation of theta, we're going to have to set one loading or discrimination to 1. And we just talked about this for the mean. Under both of these cases, the model data likelihood is identified, meaning we can derive estimates of theta and all the other parameters from it. Unique estimates of it. Right? If we didn't do this, the model data likelihood would need to be identified by the prior itself, or a set of other things. I call this strong identification. And I'm going to begin with a single dimension, as it's easier to show. The multidimensional model becomes more difficult, as you would imagine, because of the implementation in Stan. We have to figure out which item we're going to set to 1 for the loading. Okay? So let's take a look at the model block here. Here we have an item. It follows the ordered logistic, like we saw before. Again, we have our lambda. Now our lambda, remember in the multidimensional model, we had the lambda and we had init lambda before. Turns out Stan is not really good. You have to use transform parameters to fix one of these to 1. So the set of parameters we're estimating, I'm calling init lambda. Right? So here, with our data, we know we have 10 items. Init lambda, we're estimating 9 factor loadings. The lambda itself right here has all 10, but the very first factor loading is set to 1, and the remaining 9 are estimated. So it looks like this part that I've highlighted here looks identical to our previous code. The big difference is the prior is only applied to 9 of those 10 loadings. Okay? Another part that's different is theta now follows a normal distribution. It's univariate, or this is unidimensional, and its standard deviation is highlighted right there. So now we're estimating the standard deviation, and because we're estimating the standard deviation, we have to give it a prior. Actually, we don't have to give it a prior, but it works better that it does. And just to spice things up a little bit, this last week of class, I decided let's give it a log normal prior. Log normal distribution. Up to this point, I've used exponential distributions for variances or standard deviations. The exponential distribution has one parameter, the rate. The log normal has two, which means it's a little bit more flexible of a distribution. Yes?
Do we have to use labels there, or can we use the numbers directly? Because those two objects are 0 and 2 later.
Yes.
But you define those objects there and also in the data section.
I do.
You have to do that?
You don't have to. You can hardwire it. I like putting these in because oftentimes when we estimate a model, if it doesn't converge, we may want to change them. And if we put them in data, we don't have to recompile stan. Whereas you'll note here, the hyperparameter for theta is fixed to 0 because the way that stan is coded, if I allow it to be anything other than 0, we have estimation problems. Actually, that's not true. I can go and put it somewhere else, but it's rarely done where we actually fix the factor mean to like 100 or something like that. So I hard code the parts I don't want to have changed. That make sense? Okay. So next, the parameters block. This is where we again have n minus 1 lambdas. Everything else is the same, by the way. Oh, pardon me. Standard deviation has a lower bound. I forgot to put that in and things blew up on me. Now, we saw in the multidimensional case, the transform parameters block was where we had to put constraints in. Transform parameters, there we started with a matrix of zeros, and wherever our Q matrix was, we put in our estimated lambdas, right? This time, we're starting with a 1 for the very first lambda for our marker, and we put in our rest estimated below it. So that's what's happening here. The very first lambda is set to 1. That's our marker item. By the way, I could have picked the 12th. Oh, no, I can't pick the 12th. There's 10 items. I could have picked the third item to be a marker item. I picked the first, just by chance. This mirrors a lot of the other software that you see. It defaults to the very first item that appears in the data on a factor, having a 1 for that parameter. The rest get estimated. Then, the other thing I will note here, with a marker item, if you have an item that has no relation to the factor, the marker item technique will cause lots of problems estimation-wise. Because that item, you're sort of inflating its variance. So the factor variance is a function of the first item's variance itself. And so if it has like 0.01 relationship, if that parameter, if you were to do a standardized factor, was 0.01, you can imagine that 0.01 making the variance super big, and that causes all sorts of estimation problems. So it can be the case in practice that you get weird estimation when you do this. It's rare that you find an item that has such a low loading, but it does happen. So just know if you start to do this and it doesn't work for you, you can change the marker, which item is a 1, and it may work better. But you can't tell that easily before you start to do the analysis. At least I could, maybe you could. Okay, any questions? Talk data. The data block pretty much looks the same. I now have a prior for the, I have a mean and a standard deviation prior for that log normal distribution for our theta. And the R data list here, by the way, can't see it here. Shoot. Well, I'll have to fix these slides, I'm sorry. Here I'm setting the theta standard deviation mean of the log normal to 0 and the standard deviation to 2. What that really means is if you look at the log normal distribution, like if you go to Wikipedia and you see what its expected value and its variance is, to try to understand what a uninformative prior might be. It looks. I don't want the mean to be 7.39, but when I do this, the standard deviation of it turns out to be like 54, right? So It's a very flat and uninformative prior when I do that. It just happens the mean gets pulled out a little bit by the log function. So here are the results. You see our estimates. First of all, convergence was not only achieved, but we rocked the convergence here. Let me just note it, or do I have it? Yeah, there it is. Maximum R hat of 1.004. That's pretty darn converged, right? That's a good number. The theta standard deviation was estimated to be 1.73. So now 1 unit of theta is not 1 standard deviation, right? So when we talk about, yeah.
Sorry, but what's the scale of that 1.73? What's the scale, the data scale or the model scale?
It's the model scale. It's all in logits.
Right.
Yeah, because we're in a ordered logistic framework, so that would always be logits for us. So here what you'll see is before our factor loadings were between 0 and 1, mainly because of the way we standardized the factor. Now they're bigger than 1, and that's because our standardized factor, or non-standardized, the factor variance means 1 unit is now not 1 standard deviation, right? It's only 1 over 1.73. What is that? Not a little more than a third, or a little more than, oh my goodness, I'm blanking. Yeah, a little more than a third of a standard deviation, right? A little more than, sorry, it's more than half. It's 0.6 of a standard deviation or so, right? So what do I mean by that, right? The factor loading is the increase in logits per unit of theta. 1 unit, one value of 1, theta plus 1. But plus 1 now is 0.6 standard deviations, right? So it changes the metric, or changes the size of these lambdas accordingly. You can rescale them if you want. In fact, if you look at like output from Levon or M+, by default, you can ask for standardized versions of this. And there's a standardized version based on the latent variable that basically goes and gives you the value as if you had standardized the factor. In fact, we could do that in generated quantities if we really wanted to in Stant, but I didn't. Okay? How are we doing with this? Is it making sense? So? Anybody online? Everybody okay? By the way, this is the posterior trace plot of all 4 chains for the standard deviation. If you remember when I left off the last class last time trying to estimate it, it was all over the place. This looks converged, right? Looks pretty good. That's the indicator. Convergence in Bayes can sometimes be an unidentified likelihood, right? And the way that we always fix it is, oh, let's tighten our priors, but it could be the likelihood. Bayes can hide non-identification using priors. I can show mathematically this is an identified likelihood, though, so we don't have a problem with convergence here. Any other questions? Yes?
So is convergence when lines are mostly flat? Because the
Yes.
other convergence we had were like 1 minus top, then an empty space, and then
Yeah,
it's very good.
we want things to not see we don't want to see a trend here.
Okay.
What we see here is all 4 chains are sort of intermixed on top of each other. So what we'd say is the between chain variance and the within chain variance is roughly the same when this happens. That means that's our standard for convergence. If we see a trend for one of the, like if one of the chains all of a sudden flipped down and then flipped up, the between chain variance would be bigger than within, and that would be not good for us. Thank you for the question. Yes?
Could we use the PPMC to evaluate if this is right, or just the R hat?
Well, PPMC is always model fit, but not convergence. So if you don't have convergence, PPMC will not do a lot of good, right? Because technically the model parameters mean nothing without convergence, right? They're sort of garbage. Convergence without, that's always, if you look at all my examples, I always put max R hat first because I wanted to emphasize, always check convergence before you do anything else with it. And here's our distribution of theta standard deviation. I mean, you can call it quotes. It's sort of a fake standard deviation, right? I mean, heavily based on that first item's variance. Not entirely, because the other items are contributing too. But a lot of it comes from that first item's variance. Have you seen this before? I'll bet in IRT class you didn't do this, though, did you? Did you estimate theta's variance in IRT? Because this is a graded response model, which is what you probably took in IRT. But I wanted to show this to you with the graded response model, because often when you see marker items, it's with the CFA distinction, like in factor analysis class. I'm trying to emphasize the generalized modeling perspective. You don't have to have normal items to make this work. You can have Bernoulli, you can have categorical or multinomial. Right? So this is IRT where you're estimating theta's variance. Cool? All right. I'm just going to compare and contrast the distributions of theta. The green line right here, that's from our standardized factor analysis. Like, so when we had the mean of 0, variance of 1, the red is from our marker item where the standard deviation was 1.7 something or other, right? And you can see if you took the green line and spread it out, it looks like the red line. It takes a little thinking. It's almost like a Raven's progressive matrices task or something like that, right? Where you've got like a cognitive psych experiment here. But what we've done, we haven't changed the ordering of theta. We haven't changed, we have changed people's point estimate. Their EAP estimates of theta are different, but the order is the same. All we've done is rescaled it. We've changed the x-axis of it. Right, so it's the same, pretty much the same stuff. And if you wanted to compare the EAP estimates, another psych test, clinical though, Rorschach correlation. What's your correlation here? 0.999, 1, something like that, right? The estimates of EAP for the marker item and the standardized factor are almost perfectly correlated. But the difference, if you look at the range of the axis, right? X-axis goes below -2 and up to 5, whereas y-axis goes below -1 and up to a little over 2. Right? We've just literally changed the scale of the axis. That's all we've done. Right? So it's equivalent. Now the posteriors are, because of the way we've defined posterior distributions, we're not guaranteed to have the exact same shape of the posterior. They may be off a little bit, but they're pretty close, particularly the center. Here's our standard deviation estimates. We would expect some change in these, right? Theta's standard deviation is related to how much variation in theta is, right? So if you take a person's standard deviation on the standardized factor of somewhere like 0.25, right here with these dots, it's bigger under the marker item. And that's because the marker item has a bigger scale, right? So 0.25 when the standard deviation of theta was 1 is the same as 0.6 when the standard deviation is 1.7, something like that. So just broaden the scale. The lambda estimates are also highly correlated as well. And you'll note this one down here on the marker item is still our marker. It just shifts where each one's value goes. Right? This is like the anchor of the marker item, this very first item's standard deviation, or lambda. What do you think? When I was in your shoes, I'm like, I'm never using this. Right? How many times in my life have I said, I'm never going to do that, only to have to do it a week later? All of them, right? So I'm teaching you this because there will be times in your life that you may need to do this if you're in psychometrics. I much prefer the standardized factor. It sort of makes things nice in my brain, but it doesn't have to be that way. And if you didn't have me or didn't grow up in a standardized factor area like we have here in ed measurement where we often see standardized factors, you wouldn't think that way. You'd think differently for it. Okay? You want to see this in multidimensional models? Now remember that multidimensional syntax was ridiculous before. Right? We had a Cholesky decomposition to get a correlation matrix. Turns out that correlation matrix now becomes a covariance matrix if we estimate the factor variances. The diagonal of it is where the factor variances show up. So, turns out, if you know what the factor standard deviation is, if you take a correlation matrix, multiply it by a diagonal of standard deviations before the correlation, so pre-multiply by it, and post-multiply it by that same diagonal matrix, you end up with a covariance matrix. So what we have to add to our code is a vector of standard deviations that we then diagonalize and pre and post multiply to get correlations. And of course, doing that with Cholesky makes it one step further. We actually don't have to do the pre and post, there's functions built in. But that's the thing, okay? So here, again, this is pretty much the same code from before. The theta, here I actually submitted the mean vector for theta just because of the way Stan works. These are all zeros. But here, note in the multinormal Cholesky, instead of having correlation where we had before, we now have the theta cove. And theta cove L. Remember what the Cholesky did? We took a square symmetric matrix and turned it into a triangular matrix, a lower triangle. It's going to look like that. I'm trying to. You know what I can do? I brought it today for this purpose. It looked like this. If this is our matrix, all the numbers were right down here, right? This is where, this right here is the lower triangular matrix, right? Everything up here was a big zero, right? So our Cholesky does that. We use the multinormal Cholesky because of the computing issues that we have with it. Theta cove L actually gets constructed in the model statement. So here, theta cove L, we use a function called diag pre-multiply, because Stan knows we're going to do this. This is a very common thing we do in models, not just in measurement models, but in other ones. We have a covariance matrix that we have to build from a set of standard deviations and a correlation matrix. So it has a pre-built function called diag pre-multiply, where we put our vector of standard deviations for each factor, and we put our correlation Cholesky lower triangle. And that builds the lower triangle for our covariance matrix. And then finally, now we need something to talk about the standard deviations. I'm again giving it a log normal prior with a location and a scale for the log normal prior, just like we had in the unidimensional case. How are we doing? I feel like you're glaring at me. Okay. Templin, you've done it now. That's what it looked like. I look out and people are like, you SOB, you did this the last week of class? What are you talking about? Maybe I'm just reading too much into that. Sorry. I said this is a no BS class. I've broken that. Sorry. So finally, we need the correlation again. I'm still using that LKJ prior with the Cholesky. LKJ actually makes Stan a joy to use. I know you may not believe that now, but if I made you do JAGs, all of this would be way harder. Promise me. I mean, I promise you. Don't promise me anything. And I do this because I care. I just have to talk about Choleskys now. Then finally, we have our initial lambdas. Now, our initial lambdas, we're going to do a two-factor model here. Remember, we had two factors before. Each item only measured one of those two factors. So our initial lambdas are no longer 10. It's 10 minus the number of factors we have, because for each factor we have to set one of each lambdas to 1. So this init lambda will only have 8 estimated lambdas in and 2 fixed lambdas. Okay? All right. The parameters block shows that. The initial lambda has n loadings minus n factors. And loadings I grabbed from the Q matrix again. Remember I made this code where you could just give Stan a Q matrix, it sifts through the Q matrix to make its work happen. We have our Cholesky factor core for our theta correlation. And we have our vector theta standard deviations as well too. The transform data block, that is where we process the Q matrix. The additional processing here is to determine if an item should be the marker or not. Right, so now this loading location matrix I had before, which told you which row and which column to put a loading in, has two other bits of information in. In the third column of it, it takes a value 1 if a loading should be the marker, and it takes a value 0 otherwise. And in the fourth location, it is equal to 0 if it is not one of the estimated lambdas, or it's equal to the number of the lambda, like which one of those 8 needs to go there. Because now we have to not only determine which one is going to be a marker, we have to know which ones are left, right? Or we have 8 estimated. That's a mess. I don't know that I could even slow that down and make it more understandable. I'd have to I don't know. Trust me on this, right? This code, by the way, took a while to build. So if you're working on your project, you probably know my pain, right? The transform parameters block is where we fill that loading matrix up. So here, we go through each of the loadings. This is estimated or not. This is the total 10 loadings. And we say, if the third value is 1, it's a marker. So we give it a value of 1 in the corresponding row and column position of that loading based on the Q matrix. If it's not a marker item, then we go to our estimated lambdas and we take the next lambda in the sequence and put it in the row and column position according to the Q matrix. So every step of the chain, you have all of your 8 estimated lambdas in a vector, and this goes through and processes them, and it puts them in this lambda matrix, where the very first entry in a row will be a number 1, and the rest will be the estimated values. Cool? Maybe not cool. On degree of difficulty, what would you say this is? This is like, nobody looks that challenged. I'm telling you, this is some tough stuff, I think.
It's a double black diamond.
It's a
triple black diamond, experts all there.
No, I was gonna say, I was going with a number like a diving, swimming in the Olympics, right? Or the diving, the divers, right? Gymnastics. This is like a triple backflip with a twist or something. I don't know. But I say this because this is not like, if you rolled out of bed, I don't expect you to do this. Like I did this, it took me a while to do this, and I've been at this game for quite some time, right? So recognize it's not always easy to do. But when you slow down and you take each part, make yourself notes. I would encourage you to look through this, try to make yourself notes with it, see what's happening. Replicate what I'm doing in Stan and R to see what it's doing. Would also help. Right? Take a Q matrix, put in try to translate this code. Basically, this is R code without the semicolons. Actually, semicolons won't even bother you in R, without the comments. But if you did this in R, this will show you sort of what's happening, how it's sorting the Q matrix and figuring out which loading goes where. All right. And then the generated quantities block, of course, we got to have generated, right? This is where we're going to calculate our theta correlation matrix, because we want to see how correlated our thetas are. And also, if we wanted to, our theta covariance matrix. Now, often I don't care about covariances. They're very hard to interpret. I'd rather take the correlation. And so if you give me a set of correlations and a set of standard deviations, I'm really happy. That's all the information I need. But I'm just doing this to complete the training here. And in the data block, we keep going, right? More and more code. It's a code explosion. The data block, the main thing difference here is the input of the hyperparameters. And I did it again, of course. All right. And the R data list looks pretty much the same, only now we give it a vector for each of these hyperparameters. And now here's the output. Number one, this thing didn't converge as well, 1.08. Now I didn't run it long, but here's where the issue of the convergence is. These are all the parameters we tend to care about. Right here, the correlation still had to be a hard problem. 1.07 there, max R hat's 1.08. There's probably another parameter I'm not listing here that does it. But 1.07, one of the reasons for this is what we saw when we went multidimensional before. Remember, the correlation was near 1, and this correlation value is 0.989. We're going to have a real hard time estimating that. We're going to have to change some priors around, or we could just believe, yeah, these are pretty much unidimensional data. Turns out our next lecture, we'll be able to tell if it's unidimensional or not, because we'll get into model fit. But the theta covariances are right here. These are the rescaled correlations. The diagonal is 6.07, that's the variance of theta 1. 3.11 is the variance of theta 2. 4.23 is the covariance between theta 1 and theta 2. And if you're like me and don't think in variances or standard deviations, the two standard deviations are above here, 2.44 and 1.75. And then when you look at the loading matrix, you can see here's a marker item that's set to 1, here's another marker item that's set to 1, and we have our estimated factor loadings throughout as well. You will also note the following. Last time the standard deviation for the factor was 1.7 something, now it's 2.44. This is a different model. We don't have all the same items measuring factor 1, so that factor standard deviation is different. We can't expect it to be the same. 1.75 is the second factor standard deviation. So, any questions on any of this? Ready to move this on? You're just like, woo, this is great, let's go. By the way, if you're filling out your survey, remember the good classes. Just remember the good classes. Or think of it this way, I am not teaching your present self, I'm teaching your future self. Okay? Okay? And just as a reminder, if you come to my office hours today, I found the greatest rating I ever received in a class ever. At KU, I told my students I'd love it if you drew something in the text box. Somebody drew a picture of like a Godzilla attacking a building and said class was effing awesome. And then that student was in the next class and did it again. And I have it framed. So anyway. But just remember the good classes when you fill out your ratings. All right, any questions on marker items? For those of you who are doing CFA, or structural equation modeling, we're doing simultaneous analyses, which I encourage you to do if you're going to do something with your latent variable. Marker items are what you'll have to do. This is the code you'll focus with. If you're doing multi-level models, you won't need a marker item, but the code I showed you for how to do a covariance matrix. Like if you think about, if you have a, multi-level model where you have a random intercept and a random slope, and you need the covariance matrix between them, this code right here, for how you, if theta were your random values, that's how you'd build it. Now, it would not be the same here, but it would be the same above. There's slight differences to the model itself. But multi-level models and factor analyses are very close together. Okay? All right. Do we dare go for the last lecture of the class?
Let's do it.
Let's. I like that enthusiasm. I'm enthusiastic. Let's finish class.
enthusiasm so much as resignation.
But this thing, we get through this today, you can have Friday back. I can make it so I have open time Friday. You can just come to my office. We can visit. We'll have Argentina playing, who are they playing? Netherlands. That's right. We'll put that on the TV. All right. Just make it relaxed. No big deal.
Snacks?
Okay, sure. What do you want? Just send me a snack list. I'll bring it. Just fill your ratings out. All right, here we go. I'm teaching your future self. Sorry. Okay. And by the way, just make a mental note to your future self. Come back to the YouTube videos and relive. Hello, future selves. Welcome back. It's great to have you. We missed you. You've changed so much, but you look great. So, anyway.
That's why you get so many views.
Did you ever see the Blues Clues guy give that little
Yes.
I don't know. Did any of you grow up with him as Blues Clues? Yeah. Oh, you look. Yeah, Steve, you look great. Now I was already in college when he was doing his thing, so I didn't really get it, but I felt like I'm doing a little bit of that. All right, welcome back. All right, let's talk about this is model fit. We can do PPMC and we can do leave one out and WAIC. Now there's a catch. PPMC, what I'm going to show you here, there's no question it works. Leave one out, WAIC. I personally struggle with whether or not this is the appropriate way to do it. I'm going to show you how to do this based on conditional likelihoods. A lot of model fit that we do in latent variable models is on marginal likelihoods, where we remove the latent variable. I'm not doing there because I honestly go back and forth in my head, and this is an open research question. So if anybody wants to engage in research after class and wants to just do some more Bayes, this is a topic I'd love to have your help on in studying. But it doesn't have to be that. I know you're overwhelmed. Put that off till January. Or January 10 years from now. I don't care. So, you know our data. We're staying with graded response today. I gave you links to the unidimensional and two-dimensional models. We are going to compare the uni and two-dimensional models because we'd like to know which fits better. I believe unidimensional should fit better, but let's find out. So posterior predictive model checking is an absolute model fit metric. Remember, checking whether the data fit absolutely. And if you remember from the linear models course, what that meant was we generate a bunch of simulated y values, and we check to see if y's mean is somewhere in the center of it. Generate every step of the chain. We generate data for our observed variables, and we take summary statistics of them, like means. And then we see whether the observed statistic falls in the distribution of the summary statistic. For latent variables, not what I wanted. Oh, there we go. How's that? For latent variables, turns out we have to do this for every one of our observed items. So in this example, there are 10 items. So every step of the chain, we're going to generate simulated data for all 10 for 177 people. All persons, all items. It's a lot of data we're creating. So the summary statistics, typically we look at univariate measures. These aren't helpful in psychometric models. The only reason they would be helpful is if we have some really crazy priors that we put on our statistics. Or we use cross-item constraints like you see in, a Roche model, right? Where one item might influence the fit to a different item. We want to see each item by itself. But if you think about what our model is doing for each item, it's a separate logistic regression. So it's going to adapt to each item. All the parameters are unique to each item. So the only way we can really screw that up is some pretty bad choices of prior. Right? If we're like, no, my factor loadings, I know they're all 1 and the standard deviation is 0.0001. Yeah, the univariate fit is not going to be good. But apart from that, generally speaking, it's going to be pretty good. It's pretty useless. Item mean we could use, if you have categorical data, you could actually use a chi-square. If you think of your observed data for each, for us we have a 5-point Likert scale. That's your frequency observed for 1, 2, 3, 4, 5. We generate data, that's your frequency expected in each iteration. Make a chi-square out of it if you wanted to. There's a lot of different measures you could use for it. Now, in latent variable models, the most important things are bivariate measures or higher. Bivariate in terms of second order moment, third order moment, or further. If you don't know what that means, think correlation is a bivariate second order moment. If you have binary data, I much prefer using something called a tetrachoric correlation. If you don't know what that is, it's a correlation that's unbounded. In binary data, your correlation has an upper and lower bound unless certain conditions are met. Tetrachoric is one way to remove it. For polytomous data, the version of tetrachoric becomes something called a polychoric correlation. And I wanted to build that for this example, but it broke because we don't have enough people. And just like if you did homework 3 and you had a problem with one of the items because somebody didn't provide a number 5 on item 16, turns out if we generate data randomly from our model, and we don't have a lot of data to begin with, we may not have somebody in a category. Yes, our polychoric function is going to, we'll have to build a lot of code in to fix it. So I just showed you with Pearson correlations. Now I have a debate in my head. I'd love to do more research on this. I know research has been done. It's never satisfied my questions about it though. If anybody wants to do some research when everything settles down and try to study this, please let me know. Because, yeah.
For tetrachoric correlations, I'm having trouble to imagine data that can be binary but not bounded. If you can only have 2 values.
So let me do a little drawing here. The tetrachoric correlation, the Pearson correlation, actually I should say, the Pearson correlation between 2 binary variables seldom goes up to 1 or -1. Only if the marginal frequency is both 0.5, you get that. So what we end up doing, if you think of x1 and x2, if we build a contingency table here, right? And this is the probability of 0, 0, probability 1, 1. Now these are all probabilities. What a tetrachoric correlation does is it pretends there's a multivariate normal distribution that underlies these variables, right? And so this is my bell-shaped curve. Let's zoom in. Let's fly over the top of the bell. The mean, I'm going to draw contours, the height of that distribution. So this is like, let's say 0.5 correlation maybe between x and these 2 underlying variables. What the tetrachoric does is it says if I cut each of these at the marginal frequency so that in any one dimension the proportion of people above the line is like the marginal proportion of people to the 1, then the tetrachoric correlation is the correlation of this distribution that underlies. It's really away from data, but allows us though to let that distribution, we fix the mean of it to 0, we fix the variance of it to 1 for both dimensions, and we just estimate that correlation. And as the correlation changes, the proportion of people in each cell, this is pi 1, 1, if we took like the proportion of people under the area of the curve there, this would be pi 0, 0, and then the other off-diagonal cases. What we can do is find the correlation such that these proportions align with the proportions in this matrix right here. So that's a tetrachoric correlation with a 30-second intro. How's that for I'm sorry, I'd be happy to talk more about it. If you have questions about it, just come see me after class or some other time. I'd be more than happy to talk about it and spend more time on it. I know in grad school, I got the 30-second intro and it went like, I didn't really get this until I was a faculty member. So, but cool? All right, going back. The other problem with PPMC is that there's other problems with it. We don't know which statistics to use. Everybody seems to have a different favorite. I like tetrachoric, but other people like Pearson. Okay. There's no standard by which it should fit. Like, how do we know it misfit? You know, if you look at a tetrachoric correlation between items 1 and 2 and you find that the distribution's here, but your observed value is at the 95th percentile, is that misfitting? Is it just chance? We don't know. The other part of this could also be, we don't have a lot of data here. So we're going to take a correlation between item 1 and 2 with 177 people and treat it as that's the true value. When really, that's a kind of a hard assumption. There's variability in that estimate, right? So there's no comparison. Zhihang, who often attended this class, he's not here today, but just graduated. His dissertation was on looking at what happens when you don't want to believe the reference statistic is fixed and you use the distribution for it. He did a paper in SEM. If you want to click it, actually click on the link, it actually shows up. Here's the paper. There you go. Model comparison approach, PPMC. Anyway, so there's a lot to it. The other problem with PPMC is PPMC will always get closer and closer to your data if you add more parameters. So if you take a ridiculously heavily parameterized model. Now, I'm one who loves parameters, so I'm not going to go and throw stones because I love complex models, right? As you can see with my stand code, right? But it's not, if I fit a 5-dimensional model and a 1-dimensional model, it's just going to get to a certain closeness of fit, but it will not tell you which one's the most if it's valid to have it, to have those extra parameters, right? So fit only improves with PPMC. So I look at PPMC as one of the statistics you need. You need your data to fit absolutely, and then you need to potentially compare other models in a relative sense. So right now we're going to do PPMC with unidimensional and 2-dimensional models, and we're going to see model fit from it. But we'll be left with the question: is it really better? Not so sure. And then we'll go to relative model fit. So to do PPMC for 1 theta, we have to generate in generated quantities. We basically have sim y. We create a new data set. This is a new data set per iteration. So remember, we have 10 observed variables and 177 people. That's 1,770 new data points per iteration that we're saving. So our object in R is going to get really, really big from Stan. We don't have to use Stan for this, but it tends to work out pretty well. Then this model uses ordered logistic. Turns out there's an ordered logistic, RNG. RNG stands for random number generator. So what happens is we just put the same model we have in our ordered logistic into the ordered logistic random number generator function, and it will generate at random a new observation according to our ordered logistic model. It's really simple, relatively speaking. This is like a no degree of difficulty, right? It's like 1 line of code. There's no Cholesky, there's nothing else. In fact, when you go to 2 thetas, there's still no Cholesky, right? The only thing, the difference between the 2 models was how I was saving my thetas in a matrix, how I was saving my lambdas in a matrix. I just literally copied the terms from the ordered logistic model step and put it into ordered logistic RNG. How's that sitting with you? Pretty quick. So then I decided to not use Stan to process my data. Instead, we are going to process the data in R. For that, mainly because when we have a lot of these statistics, I was actually hoping to implement the tetrachoric, and it failed. I can't do a tetrachoric in Stan, so I'm just going to show you. So I use Stan to generate the data, and then at the end of Stan, I go into R and I extract the sample values from Stan and I analyze those. So here I am taking the sim y values from Stan, saving it in a matrix. And then to save, I'm going to have to save I'm going to save the Pearson correlation for each item. I'm going to save the item mean. So if I think about it, how many correlations do I have? I have 10 choose 2 correlations. So this n pairs tells me how many pairs of items I have. So I'm going to create a matrix that has the number of items pairs, and I'm going to label that by which correlation shows up. Item 1 with item 2, item 1 with item 3, and so forth. Then I'm creating a PPMC samples list. The list lets me save the correlation and the mean, and I loop through each one of my new data sets generated from Stan. I create a data frame out of that data set so I can process it in R. That's what this step right here and right there is doing. So at the end of this step, for one iteration, I have a 177 row, 10 column piece of data. I calculate the mean for each of those data frames, and I calculate the correlation for each of those data frames. And I'm only saving the lower triangle of the correlations because those are the non-redundant ones. This does not include the diagonal that involves the 1. So now what I've done is I've taken 177 by 10 data sets for every iteration and changed that into 10 through choose 2 correlations for every iteration, and then just 10 means. And now I can figure out for each item where the observed statistic falls on that distribution. In R, there is a function called ECDF. It's called Empirical Cumulative Distribution Function. What it will do is it builds into this object right here, makes this object like a function. Tempdist becomes a function where if you give it an observed value, it returns the percentile of that value. So we can tell what percentile our observed mean is from our posterior predicted distribution. The rest of this is just processing. I want to get to what I mean by that. Here is the posterior predicted distribution of the mean. This is the mean for item 1. This black line is from the samples from Stan. The red line is where our observed mean happened to be. And this is the same with 2 thetas. You can see that the shapes of the distribution changes slightly. And now this is the output from the mean results. Here I took the PPMC mean. That's the mean of item 1's means, that the mean of this distribution across all the samples. I compare it with my observed mean of 2.36. I can create a residual value from it. And this last column of the percentile, this says the observed mean is at percentile 0.58 or quantile 0.583 of that distribution. So why I'm saving that last one is that tells me if my observed value is in a tail, right? If this number that's highlighted is like 0.99, it means it's bigger than 99% of the others that I've sampled. If it's 0.01, it's less than 99% of what I sampled. So this allows me to search and highlight the misfitting observations. But do you see anything here that looks misfitting? Item 6 is at 0.61. It's still in the center. By misfitting, I'm going to be looking for extreme observations. I'll show you what that looks like with correlation. But this is a univariate statistic again. And this is where I was telling you before. This is the pattern you typically see with univariate statistics in psychometric models where there aren't cross-item constraints, like Roche, or there aren't ridiculous priors. And you know I like my uniform or uninformative priors. So none of these are in the tail. Here's correlation. Here's the pair, item 1 and item 2's correlation. The observed correlation was 0.6. You can see the distribution of correlation is quite a wide range. That quite a wide range there is because we only have 177 observations. if we generated this data set where we had 10 times that amount, sampling distribution of correlation will shrink it, right? It will not vary as much. So smaller data is harder to check for model misfit. Here it is for one correlation, for one theta, here it is for two thetas. And now, here are all the item pairs. You have item 1 and item 2. You have their observed correlation. So we thought the correlation between item 1 and item 10 here was 0.256. The PPMC correlation was 0.41. So we were actually quite a bit under the observed correlation. I'm sorry, the PPMC was quite a bit over the observed correlation here. Putting it, the percentile rank of our observed correlation was actually at the 1.6 percentile. So it's literally 98.4% of the sampled correlations that we had are bigger than this number. So I call that in the tail. It's a tail value. All right. So here, what do you do if you have all these correlations? Right? We have 10 choose 2 correlations. By the way, this dot x is the unit-dimensional model. The dot y is the two-dimensional model. So what I do, and this is not, again, yet another place for research if you want to work on something. I count for each item how many times it showed up in a misfitting correlation, thinking that items might be the problem here, right? And so I call these the bad items. So item 1, in the unidimensional model, I found that item 1 showed up in 2 misfitting correlations. Item 3 showed up in 2, and then 1 each for 10, 4, 7, and 9. In the two-dimensional model, I only found 1 bad item. It was just item 1 with item 10. What does that mean? This is what I was telling you before. The PPMC, the two-dimensional model, is slightly more complex. So it's going to try to fit the data a little bit better, and this is what we're seeing. It fits better, but it's sort of ridiculous. I also tried to plot it. This is a network plot that I was playing around with. So here I've actually plotted the groups of items. But what I do when I build if I have a bunch of items, I'm trying to think, how do I get to model fit? Sometimes I want to look to see what these items have in common. What does the 2 bad items for item 1 look like? Is there something unique? Sorry, where are the 2 bad correlations? What is that? Is there a factor I'm missing? Is there a method factor? Or is there something else wrong with it? Is it just badly written items overall? I will also go and, if I can't figure out how to make a model better, sometimes I'll just drop items. I'll do the Roche thing and say, well, the problem isn't the model, it's the data. Drop the item. We do that a lot in psychometrics. I'm joking about that, but that's like the most common strategy for fixing model fit. Oh, that item, I didn't really want that. Forget about validity of that item, I don't care. But I would take out item 1 and model fit would get better. All right, questions on PPMC? Future self. Yes?
Can you repeat please the meaning of PCT?
Percentile. That's my abbreviation. See the percentile rank of the observed correlation in this case. All right, let's talk relative model fit. Relative model fit relies upon each person's likelihood function. Remember, for every step in the chain, we needed to calculate the likelihood of a person, conditional on all their data. In a psychometric model, a person's likelihood comes from all the observations. Right? So here, we need to, in generated quantities, calculate a vector of person likelihoods. I started at 0. I loop for every item and every observation. I take the person likelihood for an observation. It's equal to itself plus, so I'm adding to it. I'm incrementing it over every 10 of the items. And it turns out ordered logistic has another function. All of the model likelihood functions have another one called LPMF. Log, I don't know what PMF is for the moment, blanking on it. It gives you the likelihood, the posterior likelihood. You have to give it the observed value of the data. So, but then after the pipe, you give it the model. So now what is it doing? It is, in this case, calculating your probability that this person, conditional on the greater response model and these parameters, the probability this person would answer with a 1, 2, 3, 4, or 5, right? 5 probabilities. By giving it the data, it selects the probability corresponding to that value a person selected, takes the log of it, and adds it to the list. Adds it to the group, the sum for that person. So it turns out this is the same function for 1 theta as it is for 2 thetas. For 2 thetas, the only difference shows up in where we put the model. Here I have a theta matrix and a lambda matrix, rather than just a theta times a vector of lambdas. What do you think? Questions? But if you calculate each person's log likelihood at every iteration, then you can use the WAIC function, and you can use the leave one out function. Using the LOO package is really what you need. So let's calculate this. The WAIC returns a value of 2965.2 for the unit-dimensional model and 2981.1 for the two-dimensional model. It does give warnings. It says, yeah, we recommend trying LOO. Well, I tried LOO and it didn't work either. But here's the fun thing about it. We pick the model, we prefer the model with the smallest value, but here we also see the standard error of that value. So if we were really comparing it, the unidimensional model has the smallest WAIC. But it's not that different when you compare the standard errors of the two. So the WAIC is going, well, yeah, I like the unidimensional, but if I talk about the variability, I may want that multidimensional model. Kind of surprising, right? I don't know. Let's talk about LOO. LOO also had problems. Now I can't show it. But here, LOO has 30.84 for the unidimensional model, 30.82 for the multidimensional model. So it's preferring multidimensional only slightly. But remember how it uses this Pareto smooth sampling, importance sampling, and it tries to tell you whether you should believe it? It's telling you, yeah, don't believe these results. So what is it telling us here? I don't know how much to trust this. This is LOO and WAIC based on what I'm reading and what people have implemented, based on the conditional likelihood. We're forming, the input to each of these uses this ordered logistic conditional on theta. Other versions of these statistics in frequentist land use the marginal likelihood, where we integrate across the space of theta. So it starts to become questionable whether we should have integrated on this thing to make it work. If we need to integrate it, that makes stand slow a lot down. We'd have to do it numerically, and it would be very difficult. But again, if you're looking for a research area, a research topic to study, I have questions about this too. I'd love to get to it. Anyway. So, questions on any of this? I did it. I made it through both. We have a minute left. Are you overwhelmed? But remember, this was for your future self. How many of you need this for your project? Try the code, then come find me. I will be, do you want to meet in class on Friday, or should we just have it be a project work day with me downstairs in my office? Or let's make Friday, I will put the project, I will send out information about where to find me, including Friday, over Icon. You'll get an email later today about that. We'll give you more lecture. But I apologize for overwhelming you. but realize I'm here to help. The slides are here. The syntax examples are there. Hopefully you can build from it. Give it a try. But I'm willing to work with you. I want to work with you. And I will also send you my schedule for times that I will be have open, walk in, whatever time downstairs. Okay? Okay, since we're not meeting, I know we're 1 minute late. Can I just take 30 seconds to thank you all for a great semester? Thank you for your work. Thank you for your commitment. I really appreciate seeing you. You're the highlight of my work life. You're the reason why I continue to have this job. I know I'm not perfect at teaching, but I hope that you got something out of this. I think at the beginning of the class, I started by saying this is a really hard class to teach. You can see why, particularly at the ending. All right? But I will say, if you're interested in doing more of this, you're welcome to sit in or even enroll in my class in the fall, because we're going to do multidimensional measurement models. And basically, it picks up where we're left off here. Last week, we did multidimensional versions of models. We will be using Bayes. We may use other things. I haven't built the syllabus yet. But I'm actually going to I'm thinking about writing a book on the topic, so I may have some chapters or things like that too. And if you're interested in more of this, we will certainly come back to the Bayes side, because multidimensional models, I find, are much easier in Bayes than otherwise. But all this was like a precursor to all that. So once again, I want to thank you. Thank you, everybody who's online. Thank you, everybody in person. I apologize for going late today. But anyway, it's been great working with you this semester. Don't forget to fill out your survey. And just remember, I was teaching your future self. Okay? Nah, just kidding. Be honest. That's all I really want. Anyway, thank you. Have a great afternoon. And I will be in contact on Icon. And then certainly, hopefully, many of you will want to present or share next Wednesday. But if not, that's fine too. So take care. And good to see you all. Thank you.